Hello everyone, welcome to this video. My name is Sentinel-2. I'm a Google Earth Engine expert. In this video, I'm gonna show you an example about deforestation in the northern Finland. So, as you can see here, recently I have visited a region in the northern Finland in a small island that all the trees were removed before. So, this is the aerial photo for the region we have been visited before, and also the reference of image is related to the Beauty of Finland channel on the YouTube, and also you can get the video for this region and to understand about the different land covers available here. And also you can see the clear-cut region in the Google Earth image. Now in this tutorial I'm going to show you how we can detect the deforestation occurred in this region through the Sentinel-2 images in the Google Earth Engine platform. So this is the location of the interest, but if you don't know where the location is, here you can see that in the northern Finland, there is a small island near Oulu, and here if you zoom in more you can find the clear-cut region among the forested region. And another important thing is that if you cannot find the region of interest in this tutorial, don't worry. The location and also the allocation address, longitude and latitude, and the coordinates information added in the example code below the video in the description box, and you can find it and use it for your own experience. And this tutorial can be used for all around the world that deforestation already occurred, and also you can use this tutorial and the data globally and freely. So in the first step I need to select the region of interest using using rectangle tools available here. Drawing tools available here, you can see that marker, line, polygon and rectangle. And the simplest way, use the rectangle to select the region of interest first. This is the first step. Then you need call Sentinel-2 images. But before that, we need to have a focus on a study area using map.centerObject. Make a new variable for Sentinel-2 images. The Sentinel equals to, through the search places and dataset, you can type Sentinel-2, two types of products available, level 2A, level 1C. Level 2A is the first choice because it is atmospherically corrected and is the best option for spectral indices. Import it into the code and import it as an image collection. Then the image collection assigned to the Sentinel variable. In the next step, we need to filter Sentinel data in a specific period of time and also the region of interest. That filter bounds your data to the region of the interest or geometry, and then through the filter date you can filter out your data based on the period of time in which Sentinel-2 image is available. So in order to monitor the deforestation for the region of interest, you need to have a historical data since the satellite data is available to understand since when the process of deforestation or the process of clear-cut started. If you go to the data description, here you can find about the earliest date the satellite data is available. It is related to 2017. Accordingly, I'm calling Sentinel-2 images from 2017 to 2024, the date or the year I'm producing this tutorial. So, for the next step, we need to call the satellite images that are cloud-free. And because it is very important to have a cloud-free images to have a clear view about the region of the interest. This is a very small region and also only in the clear images during the growing season or during the time that NDVI value is a little higher than the other months, is very important. So here, now through the filter, I'm making a calendar filter. Earth engine.filter.calendar range is another useful actually filter, allow us to actually set a specific month during a year to use the data for that. So Finland almost is covered by snow in a long-term winter, and the best period of time to study about the forest and also the vegetation cover starting from May or from June to September. That's why the starting month is number 6, month June, and the end date or the end month is the September or month number 9. And the field that explaining number 6 and number 9 is the months. So after this, we need to call those of Sentinel images in which cloud cover is less than 10%. So to get better understand about this, first print an example of Sentinel data we have called so far. So here print Sentinel variable, and then just I wanna have a limit of the results. For example, I want to see only 10 images that is called through the Sentinel variables. Because this is an example to understand if the code works well or not. There is no problem when I call the data. Here there is 10 elements. For each element we have a properties. The properties is the metadata, and in the metadata you can find information about the percentage of cloud cover in each satellite data. It is very important to call and to use the images with a low cloud cover. That's why this property allowing us to filter out cloudy images. So here make another filter, Earth engine.filter less than. I need to call the images in which cloud cover is less than 10%. So less than, and here the property or the target property is cloudy pixel percentage. I need those of images in which cloudy pixel percentage is less than LT 10 or 10%. So now I can get a print from whole images available for this period. 71 elements available since 2017 to 2024 from June to September for each year. So for the next step, we need to calculate the normalized difference vegetation index. So it's very easy. You can make a loop through that map function. That map helping us to make a loop in the Google Earth Engine platform. Then to do the calculations such as NDVI, make a new function, and each input image correspond to an IMG, and also you can choose any other names you prefer. So here, first of all, we need to select multispectral bands. Make a new variable as bands from each input image. Selected the bands starting with B letter. If you go to the data description in the bands, you can see that all the multispectral bands starting with B, B1, B2, B6, and etc. and on it goes. So those of bands starting with B selected here, and then they are multiplied to a scale factor. If you go to the data description, you can see that there is a scale factor for the Sentinel-2 data. This is the scale factor that is same for all the multispectral bands. Copy and paste it into your code. As you can see here, It's very simple, multiply it to the scale factor. Then make another variable for NDVI. Now get bands first, then dot normalize difference enables us to calculate the normalization relationship between near infrared band and also the red band. If you go to the data description, you can see that band number 8 with 10 meter spatial resolution provided near infrared reflectance in 800 nanometer. And also, as you can see here, there is another band as a red in band, and also it is band number 4 with same spatial resolution and helping us to get NDVI with 10 meter spatial resolution. Band 8 and band number 4 are proxy of near infrared and the red region of electromagnetic spectrum. Rename it as NDVI. Finally, the function returning the NDVI image with some of the properties from input images. The main properties we need for the time series analysis are system time start and system time end. That's what it looks like. There it is. So, save the code first and run it again. Again, we will have 71 elements, but this time for each date, instead of multispectral band, one NDVI image is available that helping us to monitor the deforestation in this region. So, the simplest way to see the deforestation process is get the average NDVI changes from the start date to the end. So, for example here, in order to have an accurate estimation about the deforestation, that would be better to select the region in which exactly was under the deforestation or trees cut down. So here is the regions in which the trees cut down, and I'm selecting by polygon accurately. That's what it looks like. This type of region selection help us to get more accurate estimation about what is happening in this region. So this is the main region, and also you can make some edits or modify it. So now I want to get the average of NDVI for this region from the start date to the end date. This is the simplest strategy in the first step. Throw the print, making a chart using user interface chart image.series. Couple of arguments available here. Instead of image collection, Sentinel image. Instead of the region, we have geometry and the reducer. For the reducer, Earth engine.reducer.median. The median is same as the average, but the main difference is the median not affected by extreme values. If one pixel with high value is available in the region, will have a negative impact on our estimations, because we want to get a realistic insight about the total values and the real average for the region of interest. And also we don't like it is affected by extreme very high or extreme very low values that randomly occurred in our region. So the next is about the scale. The spatial resolution for input images are 10 meter. That's why the scale should be 10. X properties equals to system time start, just like that, and run the code. In the right panel, a new chart is generating. But the figure of the chart is not very user friendly. That's why I'm suggesting to change it from the line chart to the, for example, we can change it from the line chart to the column chart. Dot set chart. As you can see, that set chart type is very useful, and here I'm gonna show the chart using the column figure. Column chart is very helpful at showing the variation of the NDVI from the earliest dates to the end dates. So as you can see, this is the forest region, and NDVI ranges above 0.5, and also that's totally normal for this region because the trees are always covered by the vegetation and leaves and foliage, and that's why we will have a higher NDVI value in this region. Moreover, the trees are provided more density of vegetation, provided more density in the region, and that's why their NDVI is higher than, for example, the croplands. So, and some of the dates like this may be missed because of the cloud cover or something like that, because since then the value of NDVI clearly increased. But after a couple of years, in 2022, you will see that the NDVI value dropped to below 0.5, meaning that maybe clear cut occurred in 2022 or between 2021 and 22. And also, if you want to get understanding, if you want to get more insight in this regard, I'm suggesting you to make a visual image for some of the years. For example, make a visual image or average NDVI for 2018 first and compare it with the 2023. That gives you more confidence about the situation occurred in this region. So here, as you can see, I'm gonna make two images. It's a very simple thing. A new image as before and after. We can make a before and after comparison. Before equals to from Sentinel-2 images that filter the data related to 2018, just like that, 2018 to 2019, and then get an average through the dot mean. Dot median is better, yes, and rename it as before clear cut, and make another variable as after Sentinel images filtered for 2023, and then get its median value during this period of time and rename it as after, just like that. Through the map.add layer, now we can visualize about what's happened in this region. So here, as you can see, first I want to visualize the before image that is clipped based on the region of interest. Leave the visualization parameter empty, and its name for layer setting is before, and use the false helping us to avoid automatic visualization that reduces the speed of processing. So map.add layer, this time for after image that is clipped based on the geometry, and leave the visualization parameter empty and use the false at the end. Run the code, and this time there is two layers. In the satellite view, you can have a better visualization. So the before image, as you can see, this is the before image for the region of interest. You can increase the contrast by 90% stretching technique. The range of values is starting from 0.3 to 0.7. That you can see the region covered by the vegetation cover, and also the white pixels showing the dense vegetation cover in this region. So, and the next one is the image related to the after, or 2023, and here I'm increasing the stretch by 90% technique and then apply it to the region of interest. Here, as you can see, clearly you can see the impact of the clear cut on the NDVI values in this region. And as you can see here, by the comparison, you will see the effects of the clear cut that occurred in this region. That's what it looks like. And also that is very helpful technique to understand about the clear-cut impact on the region of interest. And also there is one more thing, as here there is a linear relationship between the multispectral values, multispectral original values, and also the surface reflectance. You can also ignore the multiply scale factor in the equation, and also you can see that there is the same estimation, or there is the same values for the results that we gathered for this region. Then you can compare the visual characteristic again. If you want to get better insight about the comparison of NDVI in the clear cut region and also the surrounded one, you can use the rectangle here. For example, here remove the geometry just like that, and you can select a bigger region to compare to have a better comparison between the clear cut and surrounded region. Run the code again and remove the geometry, go to the satellite view, but when you select a bigger region, the values of NDVI is very close to each other, and also you cannot actually highlight the clear cut date in the plot you have estimated. So this is the before image, meaning the before NDVI values with 90% stretching techniques, and as you can see, this side has more NDVI values compared to the other side. And this is for after clear cut, and here you can see that the clear cut region clearly is detectable, and you can compare it by after and before techniques. Also, again, I use the scale factor here, just I wanted to do a comparison between using a scale factor or don't use the scale factor to see that what's happened here. So, but it is better to avoid any errors, and also the potential problems in your code would be better to use the scale factor just in case. So for the next step, we can have a estimation about the areas in which trees cut down. So here, first, let me back to the borders for the region of interest to show the clear cut date on the image. As you can see, I'm modifying the region of interest again using the polygon to limit the region of interest to the regions in which trees cut down. Yes, there it is. And run the code again to see the clear cut impact on the NDVI values clearly in this region. So for the next step, I'm gonna show you how to calculate the area of trees for the images. This is a very important technique that helping you to monitor the area of trees for this region from the start date to the end date. So now make another variable. Another variable is tree area equals to get Sentinel images first, make a loop for the further calculation, each input image as an IMG imported. Make a new variable as threshold. As you can see, the tree covers almost provided NDVI ranges above the 0.3 or 0.4 or even 0.5. That's a better range of value for each trees to separate it from the trees and non-trees pixel. So threshold equals to IMG. From each image, select those of pixels in which the tree values is greater than 0.5. To get better understanding about the situation or the threshold value, you can also use the before image and inspector tools available here. For example, by the inspector, you know that this region covered by the trees, and when you select a pixel, you can see that the before clear cut the value was 0.7, and after this the NDVI value reduced to 0.4. Just like that, you can compare it for different regions. Clearly dropped to below 0.5 after the clear cut occurred in this region. Yes, meaning that the 0.5 could be a good threshold value to separate the to separate the situation, to separate the condition we have between before clear cut and after clear cut. So GT 0.5, just like that. Now make a mask to remove those of pixels in which the threshold is less than 0.5. So from thr image dot update mask, helping us to remove the pixels in which the threshold is less than 0.5, the update mask based on the threshold again. Then to calculate the area of each pixel, we need to use pixel area function. Area equals get mask images dot multiply earth engine dot image dot pixel area. Now I'm calculating the area of pixels in which the value is above the 0.5 in all the images. So finally, function returning the area image with the properties of input images. img.property names. Just like that. For the next step, we need to visualize the sum of the area of pixels in which the threshold is above 0.5, meaning they are trees. So print user interface chart image dot series. Instead of image collection, this time tree area, because I want to show the area of trees from the start date to the end date. The region is geometry, and as I want to show the area, the total area of pixels including the trees, the reducer should be sum earth engine dot reducer dot sum. Instead of a scale, we have 10, and x property equals to system time start, and the chart type, don't forget to set the chart type as column chart. Column chart. Run the code again. In the console right panel, you will see, let me to run it again. The new chart, as you can see, shows the area of trees from the start date to the end date. And as you can see, in 2022, the area of trees in this region was around 8,000 square meter, but after this period, it's dropped to 2,000 square meter. because of the coarse spatial rate, because of the because this region is very small, and also we have 10-meter spatial resolution, we cannot have a more accurate estimation about the area of trees that is cut down in this region. If we had higher resolution spatial, higher resolution satellite data, we could have a more accurate estimation about the regions that trees cut down before. So this is an example about the deforestation. Even you can use the histogram changes for the deforestation process. As you can see, we have a before and after image here, and instead of the NDVI time series and also the area time series, you can also compare the histograms for the before deforestation or after one. It is also a very popular technique for the change detection that I want to show you before wrapping up this tutorial. So to make a separate histogram for each image, use the print first, and then in the user interface, chart and image, you will find the histogram function. In the histogram, I want to show the histogram for the before image for according to the region that is selected by geometry, and then the spatial resolution is equal to 10. Through the .set option, you can set a name for this histogram. The title of this histogram is before clear cut, and now we can have a same histogram for after image. Instead of before, this time I have after. Run the code, and finally you will see two kind of histograms. In the before image, you can see the histogram shows the histogram distribution completely changed. Before clear cut occurred, histogram shows the higher NDVI value densities in the region, but after clear cut, you can see that the distribution of NDVI values totally changed, and there is no pixels with values above 0.5 like before we had, and most of the NDVI values actually changed and also reduced, and also you can see a clear shift from the higher values to the lower values in the histogram. These kind of plots give you a very useful insight about the clear cut that occurred in this region, and it is already confirmed by the high resolution satellite data and also the aerial photo. Thank you for your attention.